This is the second problem for the in-class problems of Lecture 9, the unit on additional resistance, and here we're focused on 2D lift, the forces generated by a 2D foil. So this problem here asks, notes in the performance polars in the figure, which I'll show in a second, shows polars for 3 airfoils, and the airfoils are a symmetrical foil, a 0012 at a Reynolds number of 5 million, a 2412, which I showed in lecture, at a Reynolds number, same Reynolds number, 5 million, and that same 2412 foil, but at a lower Reynolds number. And again, for what we talked about in class is that the lift coefficients and the drag coefficients are functions of angle of attack and Reynolds number for a given foil. So what we're talking about here is what is the influence of the Reynolds number and the foil shape on the flow. So 2 foils, 2 Reynolds numbers. Let's look at those polars. This is a polar here for performance diagram, essentially for these foils. And on the left is shown the lift coefficient is a function of the angle of attack here in degrees. You can see there's three curves shown there, black, red, and blue. Drag by component is shown on the right. We'll come back to that in a second. So the first part of the question asks, which curve responds to which case? And so we will look at the lift curves here, which corresponds to which case. So we have 3 cases. The first was, I think it was the 0012 at 5 million, Reynolds number of 5 million, then a 2412 at a Reynolds number of 5 million, and then that same foil, 2412, at a Reynolds number of 5 million. And so we have, we can look at we can get some hints here. Well, let's just look at the difference between these curves. We can see that these 2 foils, or whatever these are, produce a much higher maximum lift coefficient than the blue line. So there must be some difference there. We can also see that the blue and black lines are shifted up from the red line. So everybody has a similar slope. So these all look like typical CL curves. You have a linear portion at lower angles of attack, and up as you get to higher angles of attack, you start breaking away from the linearity. So here, if I extend this up, infinitely, this line would just continue to go. We can see at some point this breaks away, and this is that stall that we talked about, the transformation to stall. The lift, increase in lift starts to be reduced until you reach a point of maximum lift coefficient, and then beyond that, the lift coefficient actually drops. So everyone has a similar slope, but we can see the black and blue line are shifted relative to the red line. If we come down and look at, so we know one of them is a symmetrical foil. That symmetrical foil, the 0012, should produce 0 lift at 0 angle of attack. So if we go to 0, 0 is occurring right here. We can see clearly that the red line must be the symmetrical foil. So that's that one is fairly easy to determine. This must be that 0012 at 5 million, the red line. So we're left with the 2412 at 2 different Reynolds number, 5 million. Oops, I wrote that incorrectly. 5 million and 500,000 was the other one. 5 million and 500,000. And so which is which? And so we can see that we know these must be the blue and black lines. We can see they're very similar in this regime, which I'll put a green box around. In this sort of regime right here, there doesn't seem to be any real Reynolds number, any significant, I should say, Reynolds number effects on the problem. So here we have Reynolds numbers that are different by a factor of 10. So that's a pretty significant range. And yet the lift curves are very close. They're essentially coincident for this foil. So we don't really see strong Reynolds effects, but then up here you can see the branching of curves. And one of these cases seems to be stalling earlier, reaches a much lower CL max here compared to up here. So after this point right here, which is somewhere around about 7 or 8 degrees angle of attack, beyond that we get a significant difference that's only due to Reynolds number. It's the same foil at the same angle of attack. The only difference is the Reynolds number. And so this brings us back to our lecture on viscous pressure drag. When we were looking at viscous drag components, we spent a lecture on skin friction, and we spent a lecture on viscous pressure drag. And what we found is that viscous pressure drag is due to flow separation, and that flow separation can be delayed if you have a turbulent boundary layer or a significant stretch of turbulent boundary layers. And so that's exactly what's happening here, is that if you allow me a second to sort of draw crudely, what's happening is that when this foil gets to some 8 degree sort of angle of attack relative to the free stream of the flow, we have boundary layers generated on this foil, and these boundary layers are formed over the foil, and they're facing at some point an adverse pressure gradient on the foil surface. That causes the flow to detach. Where it detaches and the nature of how it detaches is very dependent on the foil. Sometimes the flow separation starts at the back and moves forward. Sometimes it starts right at the leading edge, and you get a more of an abrupt stall profile. I'm not sure which is the case for the 2412 of these Reynolds numbers, so I won't specify either way. But in the case where you have largely turbulent flow over the foil, which would be the case with our higher Reynolds number, turbulent tends to delay separation. And then our case of a laminar, with the laminar foil at that same angle of attack, we have a different skin friction distribution because it's a lower Reynolds number. We have some extent of laminar boundary layer. So again, these boundary layers are forming, but they're going to, it's at a Reynolds of 500,000. It's probably nearly laminar over the entire foil. So I'll draw the boundary layer. It's a little thinner than the turbulent case at the same Reynolds number. Lower skin friction distribution. So you have a greater extent of laminar flow. However, what will start to happen is you're going to start getting flow separation in a larger wake in the downstream region. Once this reaches a high enough angle of attack, you'll have full-on flow separation, stall, etc. So the laminar case has separation first, I'll say. And so, broadly speaking, at higher Reynolds number, you can delay separation. And that's exactly what we're seeing in this little plot from X-foil, is that the only difference between the black and the blue case, let me clean up this section here, the only difference between that black and blue line is the Reynolds number, and this is the higher Reynolds number. This is the 2412 at 5 million. Oops, so right there. At 5 million. And this blue line is the 2412 at 500,000. If we were to run an even lower Reynolds number, same foil, I would expect it to follow the same linear path and then start to stall even earlier than 500,000. So this might be 100,000. I don't know exactly what it looks like, but let's say this is 100,000. What if we go in the other direction? If we say, okay, we got 5 million drawn on here, what if I went to 50 million? What would happen to the Reynolds number? I would expect it, I'll draw it with this purple line, to follow the black line and might have some benefit, but at some point the solution becomes what we call Reynolds independent, that further increases in the Reynolds number don't have any additional effect on stall or the max lift coefficient. So you don't get additional benefit to infinity. So these cases here are fairly drastically different because we're crossing this sort of transitional Reynolds number. 500,000, I don't know exactly what I had in this case, but I'm expecting nearly fully laminar flow on the upper and lower surface. Or let's say it's at least 50% laminar and 50% turbulent in the boundary layer. So laminar to about halfway down the foil. Whereas this case right here, I'd be expecting nearly the entire foil to be turbulent, have turbulent boundary layers. So the difference between 500,000 and 5 million is going to be drastically different. Beyond this 5 million to 10 million to 50 million to 100 million, the boundary layer will continue to be turbulent, and I wouldn't expect our CL max to increase significantly more to a significantly greater number. So this is just talking about Reynolds independence on lift, and I think that if I can just erase this and recap some of the key things. One is that at low angles of attack in this region here, we don't have Reynolds independence. The difference between these lines, that they're shifted, is purely because we're looking at two different foils, a cambered foil and a symmetric foil. But those two cambered foils at vastly different Reynolds, they don't produce much difference in terms of the lift coefficient. If I pick this angle of attack 5 degrees and I go up, I see that those lift coefficients for that foil at two different Reynolds numbers basically identical. It isn't until we approach stall and get into this regime where you have flow separation and significant viscous pressure drag that the Reynolds sensitivity will come into play. So at low angles of attack, when you have largely attached flow, skin friction dominates, and the Reynolds number doesn't really affect the lift coefficient. It will only affect the lift coefficient when you start to run into getting some flow separation. And the cases that you have flow separation earlier with a lower Reynolds number compared to a higher Reynolds number. On the right are shown the drag components in green, magenta, and cyan colors here. Total drag, viscous pressure drag, skin friction drag. I haven't labeled which is which, and that's part of the exercise that we're going to attempt to do. We want to figure out which is which. Which foil is which for this case. So what we're going to do is, again, I'll just write down our cases. We have a 2412 at 5 million Reynolds. We have a 2412 at 500,000. And we have a 0012 at 5 million. So we have two at the same Reynolds number, two different foils at the same Reynolds number, and the same foil at two different Reynolds numbers. So we're going to deduce which is green, which is cyan, which is magenta. And we also want to deduce which components are which. It's pretty clear, I can see right away that the total drag must be these three solid lines because they're the highest curves here. And clearly if I add the dash to the dash dot in the green, I get the total solid line here. So the solid lines are the total drag. That is readily apparent from this figure. Then the next question is which foil is which. And so I have two that are operating at 500,000. I'm sorry, one foil at 500,000 and two operating at 5 million. If I look at the 5 millions down here, well, actually it isn't as easy as I thought it was going to be. I wanted to look for symmetry, so this is zero angle of attack. I know that the symmetrical foil must produce a symmetrical pattern around that. Must produce a symmetrical pattern around the zero, such that if you go to positive angle of attack or negative angle of attack, the drag distribution should be exactly symmetrical. And so let's start with looking at these and seeing that these down here at low angles of attack, the dominant form of drag that we're going to get is skin friction. So I'm seeing, when I'm looking down at these low angles of attack, I'm seeing these dashed lines here and here are below the dashed dots, which are all clustered kind of in this little zone right here. So this tells me that the viscous pressure drag must be the dashed lines. This must be the viscous pressure drag because it starts small. It starts small at low angles of attack, but then you can see it rapidly rises right around 5 degrees here. We see those dashed lines jump up, and by the time we get to 8 degrees, they're larger than any of their counterparts. So this cluster right here of dashed dot curves is going to be the skin friction. So the skin friction at low angles of attack, around 0 here, is much larger. It's a factor of, at least in the cyan and purple curves, it's at 5 or 6 times greater than the viscous pressure drag. So that tells me the skin friction's got to be these dashed dot lines. They're the dominant form of drag at these low angles of attack. So I can tell which curves are which drag component, and the total again is these solid lines. It must be the total. Then the question of which color pertains to which of these components. And so let's see. So I have the green line here. If I look at this green line, so if I start increasing the angle of attack from 0, I can see this green line here, which is the viscous pressure drag, jumps up much more rapidly compared to the magenta or the cyan line. So I can see that increasing much more rapidly earlier. This tells me that this green line must be the low Reynolds number case. So the green is low Reynolds. This green must be the 2412 at 500,000. Because I can see that the viscous pressure drag jumps much earlier than it does in these other cases. That is analogous to what's happening on the right here, that we see this stall coming into play, and that stall is happening at the same time that the viscous pressure drag is increasing, our lift is decreasing when the stall is happening. And so this is that curve. If we look at our right plot over here, the blue curve right here is that case. And so we see the skin friction associated with that case is this green line right here. And the skin friction is less exciting. It sort of bounces around in all these cases. It's a flatter curve, whereas the viscous pressure drag, which is the regular dashed lines, starts at a minimum near angle of attack 0 and just simply increases monotonically in all cases. It increases quite rapidly once you get beyond a 5-degree angle of attack. This leaves us with which case is magenta and which case is cyan. And that's a little bit trickier to look at. And the only hint I would see here, the only thing obvious I would see here is so they're very much aligned, which tells me that the Reynolds number is similar. Their skin friction values are similar at low angles of attack. Their viscous pressure drag curves are quite similar. Not quite exactly the same, but quite similar. But one hint that I might have is if I look at the, actually there's 2 hints that I think I can see here, but one might be that when I look at the cyan distribution, I see that it is definitely symmetrical around angle of attack 0, which is that line I just drew. You see it's parabolic on either side of that, the total drag of the cyan line. This tells me that the cyan line is the 0012, because it's symmetric around that angle of attack 0. And then that leaves us with the magenta line, which would be the 2412 at the higher Reynolds number. 2412 at 5 million, I think it was. So again, it's a little bit harder to discriminate between those because the patterns are quite similar, the magnitudes are quite similar, because the Reynolds number is quite similar, and it's a Reynolds number that's driving these drag coefficients. And so the shape's playing some role in the sense that there are some minor differences between these curves. But the easiest thing I think to think about is the fact that you get this symmetrical distribution with the cyan curve, but we see that the minimum drag on the minimum drag for the magenta line, minimum total drag occurs here. That's where I'm seeing the minima, and that's a positive angle of attack right here. something like 3 or 4 degrees. That's where the drag minimum's occurring. So that's a little bit more subtle, but just sort of thinking about connecting these distributions with what's going on with these foils. So let me just clean this up and just talk through that one more time. So we have all these curves, a lot of curves here, but we're basically showing 3 different components: viscous pressure, skin friction, and total for 3 different cases. So there's a lot going on in this plot. We deduced right away that the total resistance curves had to be these solid curves at the top because they are higher, and they clearly represent the addition of the dash and dash dot curves. So that's the total drag. Then we thinking about which is the dash line viscous pressure drag, or is it skin friction? We deduced the dash line, these lower set of curves, to be the viscous pressure drag because we would expect that to be smaller at low angles of attack and grow very rapidly as we start to increase the angle of attack. The most complex curves, I would say, here are the skin friction distributions, which are these dash dot lines, which you can see are not even monotonic. As you increase the angle of attack, you see some changes that are occurring in skin friction, and that is largely due to movement of the transition point on the foil, which is responding to the pressure gradients. That transition point's moving around, which is causing the skin friction to bump around as you have different sections of laminar and turbulent flow over the foil, but it's not monotonic, and clearly it's quite complex. And then we were able to see that this green line, because the green line viscous pressure drags higher to begin with, and it increases rapidly at a lower angle of attack than these other 2 curves. From that, we deduced that's probably the low Reynolds number case, which has an earlier stall, a more rapid increase with viscous pressure drag as you increase the angle of attack. And that left us with these other 2 curves, the cyan and magenta, and the way we assign them is by knowing that one of those is from a symmetric foil, and therefore the total drag, in fact all the drag components, must be symmetric about alpha equals 0 here. So when you go to a negative angle of attack, it should produce the exact same response as a positive angle of attack. I think that's what I wanted to get through. Yes, so I will be posting these solutions written out, so you will have them. But I did want to get to this because I didn't have time in class today.